All right, so this is the handout that I'm going to put up on the website. I'll add it adjacent to the algebra part of it. Right, so the stuff I start here is things we discussed already. All right, so I won't go through these again. These are all in the fundamental handout. This is where it starts to get different. Actually, the first part is the same, the simple strategy substitution. That is the same as before. All right, this is the exact same example. But then we start talking about other things. So one strategy you could use is casework. And I'll use this example that we discussed before as well. This is an example of casework, right? Because we found that f of x, for each x, either f of x is 0 or f of x is 1, and then we took cases. Now the cases we took were a little complicated. I'll show you a simpler way you could have done that. But let's talk about this first. So when you substitute values, sometimes it's possible to identify that for some value, maybe 0, x is 0, you could identify either f of 0 is 0 or f of 0 is 1, or other values. Things like this can be possible. So in a case where you do that, where you say, well, either f of 0 is 0 or f of 0 is 1, then what you could do is suppose f of 0 is 0, see what happens, and then also suppose f of 0 is 1 and see what happens. And usually either of those would lead you to solutions corresponding to each of them. Now, another way you can do it is to sometimes you might be able to identify that. So if we can't identify what values the function takes for some domain value, it could be that this value is not fixed, right? So let me briefly come all the way down here and show you something what I mean by that. Okay, that's too far. We'll look at this in a little bit, but this is called Cauchy's equation, this equation here. In this equation, it is impossible to figure out what f of 1 is, right? Doesn't matter what you try to substitute, you will get that f of 0 is 0, right? Because if you substitute x and y are both 0, it'll give you f of 0 is 0. But it is impossible to find f of 1, and the reason for that is because f of 1 is not fixed. It depends on a constant. Well, it could vary. Basically, f of 1 is a constant, and then every other value depends on that constant. So that's what I mean by not being able to find the value for a particular x value. So in such a case, in that case we had there, it was f of 1, not f of 0, right? So in that case, f of 1 was a constant k, and then every other value depends on that. Now, when that happens, right, when you have one of the domain values or the function itself being dependent on a constant, we call that constant a degree of freedom, meaning that it's impossible to solve for that constant. So you have 1 degree of freedom. Sometimes you might have 2 degrees of freedom. It might be dependent on f of 0 and f of 1. So that will give you 2 constants or 2 degrees of freedom. What this means is that usually your overall solution would be in terms of those constants. Sometimes it might actually be able to substitute back what you have into the original equation and solve for them. But usually the fact that if they are a degree of freedom, it means that you can't actually solve it. All right, so let me show you what I wanted to explain with this question here. So we had this long explanation where we had to show that it was only either f of 0 is 0, f of x is 0 or f of x is 1. There's a simpler way you could have done that, which is when you get to this point here, you substitute x as 0. And if you do that, you'll see that either f of 0 is 0 or f of 0 is 1, right? Same thing as before, except now I'm only looking for x is 0. So in the case when f of 0 is 0, I can actually get the solution much faster than what I did here. What I could do is just substitute y is minus x up here, right? It's real to real, so I could substitute y is minus x. Or actually, a simpler thing to do is I could just substitute x as 0. If I take x as 0, I know f of 0 is 0. So this will be 0 squared is 0. And f of 0 plus y is f of y. So that would give me f of y is 0 for all real numbers y, which means that, remember x and y are dummy variables. So I could say, well, let y be x, and then f of x is 0 for all real numbers. So that would automatically give me that solution. And in the second case, when f of 0 was 1, again, I substitute x is 0, and I'll get f of 1 squared, which is, f of 0 squared is the same as 1 squared, which is 1, right? So you get f of y is 1. Right, so that is actually much faster than trying to do it using the arbitrary x and y. The general x variable, if you didn't want to do it this way. All right, so you could, again, you could just let x be 0 and then substitute 0 in here and see what happens. All right, you would eventually get the same thing. You would just be faster than what I did here. The reason why I put this in here was to explain the fact that you have to be careful when you end up with things like this. When you have that f of x is, well, f of x times something else is 0. It's not always a strict divide in terms of saying, well, either f of x is 0 or f of x is 1. It could be combinations. Right. Another strategy is to kind of use values, see what happens, and then maybe guess what the solution is, or try to, well, based on patterns you see, identify what the solutions are, and then try to reverse engineer proof. Now, if you're trying to reverse engineer proof, one way to do it is by induction. But you can only use induction if you're working with integers or positive integers or natural numbers, right? It doesn't work for real numbers. So if it's a function for real numbers, this isn't going to work. Another thing you can do is proof by contradiction. So sometimes when you have cases, you might want to prove by contradiction that one of the cases doesn't lead to a solution. So it means that the only solution is the one you got from the other case. This strategy here, start with a subset and then work outwards. The easiest way to apply this is sometimes you might be able to prove something by induction for integers, even though the set is real numbers, right? So you might want to start with the positive integers, prove that by induction, and then use a similar strategy to go for the negative integers. And then you go for maybe reciprocals, so 1 over n. And then you could do general rational numbers, so m over n, and see if you could prove that. So basically, you're building up to real numbers. Now, the thing is, if you're doing it like this, the only way to extend it to real numbers is if you know the function satisfies one of these properties. So we'll talk about it a little bit later. So this strategy only works for functions that are either continuous, monotonic, or bounded, and we'll see those definitions just now. This example we had looked at before. So iteration is another strategy. I don't have an example of it here, but basically what you do here is you apply the function to both sides of an equation, right? And there aren't many examples that use this, questions that use this. Essentially, what you're basically trying to do is, if you have some kind of relation involving the function, you might want to, and you have another relation, you might be able to combine both of them by taking f of both sides of one of the relations. So that's what I mean by iteration. Surjectivity and injectivity. So we talked about being surjective and injective, or onto and one-to-one. We could actually use those. So this is just going back over what those things mean. Right. An alternative way to prove something is one-to-one is, so the way you normally prove it is assume that f of x1 is f of x2, and then prove that x1 must be x2. You could do the converse, the contrapositive of that. You could assume that x1 is not x2 and show that f of x1 is not f of x2. Depending on the question, sometimes it's easier to do this, sometimes it's easier to do this. All right, so how do you use these things? Well, for surjectivity, how you would use that is, if you prove, first you have to prove it's surjective, but if you prove it's surjective, right, it means that every value in the domain has something mapped to it. So for example, you could say, well, let k be a real number such that f of k is 0 or f of k is 1. And the reason you might do this is depending on the question, and actually simplify the equation you have. So surjectivity is what allows you to say something is mapped to a number and try to figure out what k is. So why you would do this is to try to figure out all the numbers that are mapped to 0, and that might help you simplify the problem. So just to note, you can always, as long as 0 in the domain, you could always say let f of 0 be some number, say k z or something. So I could say let f of 0 be z and try to figure out what z is. But I can only do the reverse of that. I can only do let f of k be 0 if I know it's surjective or onto. So that's how you would use it here. For one-to-one, now one-to-one is more useful than surjective, but is sometimes not as easy to prove. Right? So for one-to-one, basically, and I didn't talk about how you prove surjective, but how you prove surjective is basically show that for every number y, there's something mapped in. So basically, if you can identify or isolate x or y or something by itself equal to f of something else, doesn't matter how complicated or complex that something else is, then your proof is onto, because f of something gives you y or f of something gives you x. For one-to-one, it's sometimes not as easy to prove because you have to, again, either assume this and then prove this, or assume this and prove that. But if you can prove it, it can help. So for example, this is a mistake that some students sometimes make, so be careful with this. If I give you this, right, or if you're able to derive this expression or this equation based on what you're given, f of x is equal to f of x plus 1. Be careful, because if the function is not necessarily injective, then you cannot cancel the f's. You can only say, well, I cancel this f with this f if you know the function is injective, right? That's important. So if it's injective, then we can cancel one of the f's and say, well, f of x is equal to x plus 1. And that's a solution. However, if it isn't necessarily injective, then your answer will be wrong. Because, for example, f of x is equal to c also satisfies this. If f of x is c, you'll get a constant here and a constant here, and that, well, the same constants, so they're equal. This is not injective, which is why it didn't get the answer when you cancel the f's. So when you cancel f's, you're actually eliminating solutions. So be careful with that. All right, so just a note here, canceling f's in an equation where f is not injective, or that where you don't know that f is injective, is the same as basically divided by 0. All right, sometimes for some questions, you might be able to show that f of x is equal to x. Once you do that, automatically the function is both injective and surjective. So it's automatically bijective. It's surjective because you have f of something being mapped to x, right? So there's something that maps to x. It doesn't matter what that something is. And it's injective because if we assume that f of x is equal to f of y, I can take f of both sides and I'll get f of x is f of y. And then using this relation that I know, that will imply that x is equal to y. Right? So that's how you would prove surjective and injective for that. If the function is defined over integers, and this is only for integers or natural numbers, then you can consider different bases. Right? So sometimes base 2 and base 3 representations help. Periodicity can also help. Reason being, if you can show that something is periodic over a certain interval, then you just need to consider that interval. For example, sine and cosine are periodic functions. So and the period is 2 pi. So by just considering those functions over a period of 2 pi, you can derive all the information you need to know about those functions, rather than looking at the entire real line. One more advanced strategy to use is fixed points. So a fixed point is a point such that f of x is equal to x, or f of x0 is equal to x0. All right. Now, if the domain and range are not the same, then they're not going to be fixed points, right? Because it has to be mapped to itself. So be careful with that. Again, I don't have any example here of how that's done, but there are several IMO questions in recent times that have used that. So we'll look at those at some point. Symmetry is also useful. Basically, if you can show, so let me give you an example. If you have a function satisfying this, right? F of x minus x squared is the same as f of y minus y squared. Remember, remember x and y any real numbers in this case, right? So x could vary and y could vary. And what it says is that if I fix x, for example, if I take x as 1, f of 1 minus 1 squared is the same as f of y minus y squared, no matter what value I choose for y. The only way that could be true is if both of these are constant. Or, well, if these things are equal to a constant, because y varies and I get the same value every time, so it must be constant. So, because it's constant, I could equate to some constant a and k, and then I could basically just solve from there. F of x is equal to k minus x squared, k plus x squared, sorry. Right, that's how symmetry works. There's an example, I think later on, that uses that. All right, now to talk about the things that I mentioned before: continuity, monotonicity. Let me say that correctly. Monotonicity and boundedness. So don't worry about the formal definition of continuity down here. Well, theorem there, or even this definition. This is really the formal definition. Basically, we say a function is continuous at a point if f of x, the value of f of x tends to the value of f of a as x tends to a. Meaning that as the x value gets closer to a, the function value gets closer to the function value at a. That's what we mean by continuous. Continuous basically means there are no breaks in the graph or no jumps, right? So you don't need to worry about how to prove something is continuous. In questions that use it, you will be told that is continuous, and you basically just use it as a condition to make a conclusion. And you'll see what I mean by that later. Similarly, something is monotonic. It could be either monotonically increasing or monotonically decreasing, or it could be strictly increasing or strictly decreasing. Monotonic just means it increases or decreases in the same way, basically. So it either always increases or it always decreases. Right, now if it's strictly, it means it strictly increases or it strictly decreases, right? If it's monotonically increasing or monotonically decreasing, it means that it either increases, like you could think of it as a step, right? So it could be equal at some values, but it could never be, the sign could never change. Basically, that's what it means. So think of a step going up. It could stay the same for some values, but then at some point it'll keep going up. So we say it's monotonic if it's either monotonically increasing or monotonically decreasing. And the last one is bounded. Bounded just basically means there's an interval in the y-axis where the function values all lie between that interval, right? Well, it's bounded above if there's an upper limit, and then it's bounded below if there's a lower limit. And it's bounded if there's both an upper and lower. So you can think of it as like a horizontal strip on the y-axis. Well, horizontal strip in the xy plane, and the function values all lie between, well, within that strip. That's what we mean by bounded. And those three things I just mentioned, they're really just used for this. So Cauchy's equation is a special functional equation here. F of x plus y is equal to f of x plus f of y, right? And this equation, if you know that the function is either continuous or monotonic or bounded, which the three things we mentioned before, you just need to know that they are that. You don't need to know anything else. Once this is true, the function, the only solution is this. F of x is equal to k times x for some constant k. K is a constant, right? So the solution is actually this. So this has 1 degree of freedom. Right, now how you would do this is, as I had mentioned before, you could start off with the positive integers. So if you let y be 1, you'll get f of x plus 1 minus f of x is a constant, right? So that's really an arithmetic progression. And you could figure out that if you let f of 1 be k, basically you'll get f of x is kx for positive integers. Then you could do it for the negative integers. You could do something similar for reciprocals and then rational numbers. And this continuous or monotonic or bounded part is what lets you expand it to real numbers. And why you can do that is because of what is called the density of rationals and irrational numbers. Between every two rational number, there's an irrational number, and between every two irrational numbers, there's a rational number. So basically, if you prove that this thing is true for all rationals, and then the function is continuous or monotonic or bounded, it is automatically true for all irrationals as well. So it will be true for every real number. Now, Cauchy's equation is a is a standard equation. This is known, so you don't actually have to prove this. Once you see the equation, you could automatically write the solution as this. Again, once you know it's continuous or monotonic or bounded. Right? And then these are variations of Cauchy's equation. So instead of addition on the right-hand side, we have multiplication. So in that case, the solution is this, a to the power of x for some constant a. And then instead, on the left-hand side, instead of addition, you could have multiplication. And the solution is log a base a of x. Now, you could use laws of logarithms and change the base and say, right, this is some constant times ln x if you wanted to. And then you can have multiplication for both of them, in which case the solution is f of x is x dot a constant c. Right, so basically, this is the important one. I mean, it is also nice if you know those. If you don't know them, then you could try to figure out what the function is to transform them to Cauchy's equation. And then once you know that, you could basically just state the solution. Right? And so why this is useful, sometimes you might have a complicated functional equation where in one of the cases, it reduces to this. And then once you reduce it to this, you can just state, well, okay, the solution is this, because I know it's continuous or it's monotonic or it's bounded. The question will actually state that. If you see a question says, find all continuous functions or all monotonic functions or all bounded functions, then you're 99% sure you're going to have to end up with this at some point and then use the solution. Well, either this or one of these. Because usually, really and truly, that's the only time you see those conditions stated. Okay, so that's it. That's for the advanced stuff. So I'm going to post this on the website adjacent to the algebra part of it, right? And I'll add the videos there as well, and I'll add the videos to the playlist so that those who didn't go into the session could view them later. Does anybody have any questions before we end?